genetic material of Majungasaurus was in possession of InGen by 2014 and was used in the genetic hybrid Indominus rex in Jurassic World. This explains the Indominus prominent scale orientation, as well as cannibalistic traits. The Majungasaurus clones are slightly oversized compared to the actual animal, but still have a fairly accurate appearance to the original creature, including the length and the position of the arms, which don't pronate like the rest of the cloned theropods in the series. Majungasaurus was a unique theropod, distinguished by its skull ornamentation, including a frontal horn and fused nasal bones, likely used for display rather than combat. Unlike some other ceratosaurs, there is no evidence of sexual dimorphism in its ornamentation. Its feeding strategy differed from most theropods, which had long, narrow skulls adapted for delivering multiple bites. Instead, Majungasaurus had a short, broad snout design for a bite-and-hold technique, similar to modern big cats. Its reinforced skull, strong neck, and robust teeth supported this hunting style. Adaptations like thickened nasal bones and flexible jaw joints helped Majungasaurus hold onto struggling prey without breaking its skull or jaw. It had rapid tooth replacement, possibly due to frequent gnawing on bones, replacing its entire set within 2 months. Majungasaurus was the dominant predator in its ecosystem, likely specializing in hunting sauropods like Rapidosaurus. Its short, powerful legs made it slower than other theropods, but well-suited for overpowering large prey. Tooth marks on sauropod bones confirm it at least scavenged them. Evidence also suggests Majungasaurus was a cannibal, as some bones from its own species show feeding marks matching its teeth. Whether it actively hunted its kind or scavenged remains is unclear, but comparisons to Komodo dragons suggest competition over carcasses may have led to cannibalism. It had an avian-like respiratory system with air sacs, indicating a highly efficient breathing mechanism. This supports the idea that bird-like lungs evolved early in theropod evolution, long before birds themselves. CT scans of its brain suggest it had a conservative, crocodile-like brain structure. Its small flocculus implies it did not rely on quick head movements for hunting, unlike some other theropods. Its inner ear structure suggests it held its head in a nearly horizontal posture. Pathological studies reveal some individuals suffered from injuries, including a case of severe tail damage, possibly due to infection or trauma. While most individuals showed no signs of pathology, a few had multiple injuries, suggesting a snowball effect, where one wound led to further complications. Growth studies indicate Majungasaurus had a slow growth rate, taking around 20 years to reach maturity. This may have been an adaptation to the harsh environment of Madagascar. Similar slow growth has been found in other abelisaurids. Juvenile Majungasaurus had proportionally larger eye sockets and less robust skulls, suggesting a dietary shift as they matured. These changes indicate they may have targeted different prey at different life stages. Carcharodontosaurus was capable of lifting up to 420 kilograms alone or 850 kilograms with a partner, according to a 2015 biomechanical analysis. Its teeth were thin, blade-like, and not suited for crushing bone, unlike those of Tyrannosaurus. However, their large size and high replacement rate compensated for their fragility. Carcharodontosaurus had a weaker bite force than Tyrannosaurus, with a maximum of 25,000 Newton. Studies suggest its skull was not built for heavy stress, indicating a preference for softer prey. Compared to Spinosaurus, isotopic analyses show it was more terrestrial and homeothermic. Its lacrimal crest function is unknown, but might have played a role in head butting. A 2006 study on vision found Carcharodontosaurus had limited binocular overlap, likely holding its head at a downward 40 degrees angle for better vision. This suggests it was an ambush predator detecting prey through motion parallax. The neotype skull shows signs of pathology, including bite marks and bone infections, similar to Allosaurus and Acrocanthosaurus. These injuries may have resulted from fights with rivals. The elongated rostrum of Carcharodontosaurus limited its forward vision but helped judge distances when attacking. Unlike Spinosaurus, it did not rely on aquatic environments as indicated by its fossils being found in terrestrial deposits. Its skull structure, with extensive pneumatic cavities, was designed to be lightweight rather than reinforced for powerful bites. Stress distribution analyses suggest it had a stronger skull than Spinosaurus, but weaker than Tyrannosaurus. Its diet likely consisted of medium to large prey rather than heavily armored animals. Evidence from bite marks suggests Allosaurus engaged in face biting, a behavior possibly shared with Carcharodontosaurus. The circular puncture wound on its nasal bone may have been caused by intraspecific combat. Taphonomic data supports that it primarily inhabited land rather than semi-aquatic regions. Despite its massive size, its feeding adaptations made it a specialized predator distinct from other large theropods. It is unknown how Biosyn obtained DNA to clone Dimetrodon, since the species lived millions of years before either mosquitoes or amber existed. Dimetrodon is thus far the oldest prehistoric animal featured in the entire franchise. It was recreated by Biosyn before 2022. Paleontologists have proposed multiple functions for Dimetrodon's sail, including camouflage, wind-assisted movement, and trunk stabilization. The most widely accepted hypothesis suggests it played a role in thermoregulation, allowing Dimetrodon to warm up quickly in the morning and cool down when necessary. Early studies estimated that a 200 kilograms individual could raise its body temperature by 6 degrees Celsius in 1.5 hours, but later research suggested a slower rate of about 4 hours. While the sail helped absorb heat, it was not effective at retaining warmth overnight. Some scientists proposed that it contributed to homeothermy, maintaining a relatively stable body temperature. This trait may have been an evolutionary step toward warm-bloodedness in mammals. However, the presence of sails in small-bodied Dimetrodon species challenges the thermoregulation theory, as smaller animals can regulate heat without such structures. The evolutionary transition from small crests in relatives like Sphenocodon suggests that thermoregulation was not the sail's primary function for most of its history. Some studies indicate Dimetrodon may have been a whole-body endotherm with a high metabolic rate, supported by vascularized spines and large blood foramina. Larger individuals had proportionally bigger sails, which could have aided in heat dissipation, but a 2010 study found the sail's growth rate exceeded what was necessary for thermoregulation. This suggests sexual selection played a major role in its evolution, similar to antlers in deer. The sail may have been used in threat displays or courtship rituals, as seen in some modern lizards with raised frills. Evidence of sexual dimorphism in Dimetrodon supports this idea, with some individuals displaying thicker bones, larger sails, and longer skulls. Differences in maxillary structure also suggest possible male and female variations. Museum-mounted specimens exhibit variations that may indicate distinct sexes. The function of Dimetrodon's sail remains debated, but a combination of thermoregulation and sexual selection is the most likely explanation. Biosyn developed a new feather system for Jurassic World Dominion to efficiently create and modify feathered dinosaurs like the Pyroraptor. The system allowed artists to place feather quills quickly, assign various feather types, and use an automatic detangling system to ensure a realistic look. Different feather textures including a large head, crest, and softer downy feathers, were implemented based on bird anatomy with a flattening zone added to adjust the silhouette. Environmental effects, such as water interaction, were a major challenge, so the team studied birds and seals to replicate realistic wet feather behavior. For lighting and weather accuracy, John Nolan Studios built a practical Pyroraptor head with hand-dyed feathers, which reacted naturally to wind during filming. Pyroraptor was cloned by Biosin and released to live within their sanctuary, where at least one individual lived atop the frozen lake held behind the valley's dam. Pyroraptor was a dromaeosaurid, a small, bird-like predatory theropod that possessed enlarged curved claws on the second toe of each foot for predation. These claws were 7 centimeters long for Pyroraptor. As in other dromaeosaurids, these claws might have been used as weapons or as climbing aids. Its 2 known teeth are flattened and curved backwards, with their rear margins having finer serrations than at the front. As a dromaeosaurid, it likely had well-developed forelimbs with curved claws and probably balanced the body with a long, thin tail. Pyroraptor was also covered in feathers, as many of its relatives, like Microraptor and Sinornithosaurus, also had plumage. The Pyroraptor is the 4th predator in the cinematic franchise who's shown to swim in order to hunt its prey. However, at least one dromaeosaurid group, Halscaraptorinae, whose members are Halscaraptorines, are most likely to have been specialized for aquatic habits. Studies of the olfactory bulbs of dromaeosaurids reveal that they had similar olfactory ratios for their size to other non-avian theropods and modern birds with an acute sense of smell, such as tyrannosaurids and the turkey vulture, probably reflecting the importance of the olfactory sense in the daily activities of dromaeosaurids, such as finding food. According to Industrial Light and Magic Senior Visual Effects supervisor David Vickery, a long part of the Therizinosaurus development was spent looking at what types of feathers it would have, which turned out to be hair-like, sparse, vein-structured feathers. This worked well with the idea of giving the feathers an oily-looking iridescent. The DNA of Therizinosaurus was acquired by InGen and was used in the creation of the Indominus Rex in Jurassic World. However, no individuals were created for the park. A specimen was cloned by Biosin and kept within Biosin's sanctuary in the Dolomites. In Italy, Claire Deering encountered Therizinosaurus after ejecting from a crashing plane, narrowly escaping by hiding in a pond while the dinosaur stalked her. Later, during the Giganotosaurus rampage, the Therizinosaurus engaged in battle alongside the recovering Tyrannosaurus, ultimately helping to kill the Giganotosaurus by impaling it with its claws. It can be assumed that the Therizinosaurus is out in the wild or continuing to live in the abandoned sanctuary, which is now an international preserve. The Therizinosaurus seen in Dominion was confirmed by the interview from David Vickery that it's blinded at the right eye, but on screen it has cloudy effect on both eyes, and many fans think it's blinded in both eyes. However, if you notice it carefully, on its left eye is more like cataract and not as cloudy as the right eye, which mean its left eye vision inefficient and blurry, while on the right is completely blinded. In 1993, Dale A. Russell and Donald E. Russell compared Therizinosaurus to the mammalian Calicotherium, noting similarities in body structure despite being from different groups. Both had strong arms, robust pelvic girdles, and shortened hind limbs, which they suggested indicated a herbivorous lifestyle. They proposed that Therizinosaurus could sit while feeding, using its long neck and claws to pull foliage from trees and shrubs. Unlike Calicotherium, which hooked branches, Therizinosaurus likely pushed large clumps of vegetation with its claws. Its long arms may have also helped it rise from a sitting position. In 2018, Fiorillo and colleagues suggested that Therizinosaurus had a weak bite force, supporting the idea that it relied on its claws to collect food rather than chewing tough plants. The claw's function has been debated for decades. In 1954, Malieve initially thought they were used to harvest seaweed, believing Therizinosaurus was a giant marine turtle. Later, other scientists suggested they were used to open termite mounds, dig soil, or even for defense. However, their fragility upon impact made active defense unlikely. In 2014, Lautenschlager tested various therizinosaur claws through digital simulations, analyzing three functions: digging, hooking, and piercing. His results showed that Therizinosaurus claws were not suited for digging, but were more effective in a hook and pull motion, likely for grasping plants. The claws also exhibited high stress under pressure, suggesting they were highly specialized. Lautenschlager could not confirm if the claws were used for mating, intraspecific competition, or intimidation. He noted that, while they may not have been primary weapons, they could have served as a visual deterrent to predators. In 2018, Lee and Richards found that Therizinosaurus had humeri resistant to stress, indicating its arms were strong and capable of exerting significant force. This suggests that Therizinosaurus, unlike fast-running theropods, relied on its claws and arms for survival. While some researchers believe the claws played a role in defense, others argue their primary function was related to feeding. A 2023 study by Cheen, Rayfield, and Benton suggested that the claws had no clear mechanical function and were possibly ornamental. They proposed that the claws resulted from paramorphic growth linked to Therizinosaurus' large body size. Although the exact purpose of its claws remains debated, Therizinosaurus is widely accepted as a slow-moving herbivore. Its long arms and claws were likely used to pull vegetation rather than engage in combat. Some researchers believe they also played a secondary role in intimidation or display. Therizinosaurus remains one of the most unusual theropods, with a body structure distinct from its carnivorous relatives. Attenborosaurus derives its name from the renowned natural historian Sir David Attenborough, who is the brother of Richard Attenborough, the actor portraying John Hammond in Jurassic Park. The holotype specimen was discovered in Charmouth in England in 1880 and described in 1881. It was housed at the Bristol City Museum until it was destroyed during World War II in 1940. Fortunately, a cast had been made before the war and sent to the Natural History Museum in London, where it is still preserved. Along with this cast, 2 additional referred specimens are also housed there. Judging by the holotype, which is the partial remains of one single specimen, the length of the animal was about 4.3 meters. Much like its plesiosaur cousins, it was piscivorous. From the skin impression found with the bones, which was later destroyed, it is presumed that the creature had membranous skin, devoid of any significantly large scales, probably for decreasing water resistances. Velociraptor is one of the most popular dinosaurs in the Jurassic Park movie media. They are often seen hunting in packs, which they are actually believed to have done in real life despite no firm evidence. They are portrayed as being highly intelligent and capable of setting traps and communicating with other pack members, such as being able to escape their paddock without Dennis Nedry's assistance. Because of this, the main paleontologist of the franchise, Dr. Alan Grant, is very interested in the raptors. It was created by InGen scientists on Isla Sorna, with early attempts at cloning failing due to incompatible poison dart frog DNA. Dr. Henry Wu later suggested using common reed frog DNA, which enabled dinosaurs to change sex and breed. In 1992, Dr. Wu studied the raptors' intelligence and communication, while 26 raptors were created, with 8 moved to Isla Nublar for Jurassic Park. A dominant raptor, the big one, took over the pack, killing all but 2, though one raptor managed to change sex and reproduce before its death. The velociraptors in the films resemble Deinonychus in appearance and are similar in size to Utahraptor. They possessed a resonation chamber in their skulls and were described by Dr. Alan Grant as highly intelligent, even smarter than primates. Raptors were depicted as strategic hunters, using coordinated pack tactics to ambush prey from the sides. While often assumed to be Deinonychus, Jurassic World's Whole Escape attraction classifies them as a separate species, with Dakotaraptor being a closer real-world match. The film's Velociraptor was primarily based on Deinonychus, with early concept art by Mark Hallett, John Gertsch, and Gregory Paul influencing its design. Mark McCreary finalized the design, creating concepts for different life stages of the raptor. Steven Spielberg requested the raptors be larger for a more menacing appearance, coincidentally matching the later discovery of Utahraptor. Various color schemes were explored, but ultimately toned down due to lighting effects. Practical effects by Stan Winston Studio included animatronics, bodysuits, and insert heads for close-up shots. John Rosengrant and Mark McCreary performed in raptor suits, notably in the kitchen scene. The original endings featured different deaths for the raptors, but were changed to highlight the T-Rex. Early animation tests used Go Motion, but industrial light and magic CGI ultimately replaced it. Phil Tippett developed the dinosaur input device to blend traditional animation with CGI. The raptors' movements were meticulously choreographed using animatics and puppetry. During the Jurassic Park incident, the velociraptors proved to be highly intelligent and dangerous predators, escaping their pen after a power outage and systematically hunting park staff and visitors. Ultimately, they were defeated when a Tyrannosaurus intervened, but their survival on Isla Sorna was later confirmed, as they adapted to the wild by overcoming genetic limitations. For years after the Jurassic Park incident, two rival teams became stranded on Isla Sorna, where velociraptors ambushed and killed many of Ludlow's men in the long grass. While Ian Malcolm and his group were later attacked inside a facility, they managed to outmaneuver the raptors, ultimately escaping the island by helicopter. While evading raptors in a genetics lab, Dr. Grant and his team witnessed their advanced communication as they called for reinforcements. Later, the raptors cornered the survivors, demanding their stolen eggs. But Grant used a resonating chamber to mimic their calls, allowing the team to return the eggs and escape as the raptors retreated into the jungle. In Genus, Vic Hoskins initiated the Integrated Behavioral Raptor Intelligence Study in 2012, officially for training but secretly aiming to weaponize raptors, with Owen Grady later hired to train a pack. In 2007, Alan Turner and colleagues discovered quill knobs on a velociraptor fossil, confirming the presence of feathers. This suggests that velociraptors' ancestors could fly, and that it became secondarily flightless. The feathers may have been used for display, nesting, or aiding movement. However, the classification of this specimen is still debated due to the presence of another dromaeosaurid, Sagin, in the same locality. Studies on Velociraptor's skull indicate it had acute hearing and was a swift predator, though it may have also scavenged when necessary. Research on its maxilla suggests it selectively fed on small, fast prey. Bite force analysis found Velociraptor had a weaker bite than related dromaeosaurids like Deinonychus. The fighting dinosaurs fossil, showing a Velociraptor and a Protoceratops locked in combat, provides direct evidence of predatory behavior. The Velociraptor's sickle claw was likely used to pierce the throat rather than slash prey. Some scientists tested the slashing hypothesis and found it unlikely. While pack hunting is often depicted in media, no fossil evidence confirms this behavior in Velociraptor, though other dromaeosaurs may have hunted in groups. The raptor-prey restraint model suggests Velociraptor used its sickle claw to pin prey, much like modern birds of prey. Scavenging evidence includes a 2010 discovery of Velociraptor teeth near Protoceratops bones and a 2012 specimen with a pterosaur bone in its gut. A 2024 study suggested Velociraptor had adaptations favoring scavenging over active hunting. It was warm-blooded to some extent as indicated by its feathers, but likely had a moderate metabolism similar to modern kiwis. Nasal cavity research in 2023 suggests it lacked advanced thermoregulation like modern warm-blooded animals. Paleopathology studies revealed Velociraptor fossils with injuries from interspecies fights, including a fatal bite wound. Another specimen had a healing rib injury and pterosaur remains in its stomach, suggesting it scavenged while injured before dying. Amargasaurus DNA might have been used in the creation of the unidentified Therizinosaur hybrid seen on a computer screen in Jurassic World. It can be speculated since the hybrid appears to have spines similar to the ones in the sauropod. Amargasaurus was a relatively small sauropod, measuring 9 to 13 meters in length and weighing between 2 and 4 metric tons. It had a shorter neck than most sauropods, a common trait among dicreosaurids, with 13 cervical vertebrae forming a ball and socket joint structure. Its most distinctive feature was the tall, bifurcated neural spines running along its neck and back, possibly supporting a sail or keratinous structures. The preserved rear part of its skull suggests it had a broad, horse-like snout with pencil-like teeth, and its nostrils were positioned above the eyes. Unlike most sauropods, Amargasaurus had small supratemporal fenestrae and unusual parietal openings, which are typically found only in juvenile tetrapods. The function and appearance of Amargasaurus' elongated, bifurcated vertebral spines remain uncertain. Some paleontologists, such as Salgado and Bonaparte, suggested they served as defense weapons or for display. Gregory Paul dismissed the idea of a skin sail, arguing the spines were better suited for supporting keratinous sheaths that could be used for defense display or even sound production. Jack Bailey compared the spines to those of pelycosaurs and proposed they supported a single skin sail rather than two separate ones, possibly forming a hump like in modern bison. Schwartz and colleagues suggested the spines enclosed an air sac connected to the lungs, while Hallett and Waddell proposed they were defensive structures capable of skewering predators. Later, some supported a defensive function, noting the related Bajadasaurus had similarly shaped spines that extended past its snout. In contrast, study by Serta found evidence that the spines were primarily covered by skin rather than keratin. Amargasaurus likely had a relatively poor sense of hearing, as suggested by CT scans of its skull conducted by Carabajal and colleagues. Early skeletal reconstructions depicted its head in a near-horizontal posture, but later studies indicated it was held at a downward angle of about 65 degrees. The neck likely sloped gently downward, with the snout resting around 80 centimeters above the ground in a neutral position. While the animal could raise its head somewhat, the elongated spines would have limited its ability to reach high vegetation. The overall posture and spine structure suggest Amargasaurus was adapted for low browsing, possibly using its unique spines for display, defense, or communication. The cloning of Quetzalcoatlus remains quite obscure. It appears to have been carried out in complete secrecy by Bayesian using fossil remains from a specimen discovered in Texas in 1971. A few specimens are kept in captivity within the company's sanctuary. During the 2022 incidents, one of these giant pterosaurs attacked a plane attempting to land. The creature appeared enormous, nearly as large as the aircraft itself. Following these events, like most animals created by the company, the Quetzalcoatlus were released into the wild. With their large wings and ability to cover vast distances, they quickly spread across continents. Quetzalcoatlus northropii was one of the largest Azhdarchid pterosaurs, with a wingspan estimated between 10 to 11 meters. It belonged to the long-necked group of Azhdarchids, characterized by slender beaks and quadrupedal locomotion. Its wings were broad, with a structure adapted for static soaring, similar to large birds of prey. Estimates of its body mass vary, but recent studies suggest the species Northrope weighed around 150 kilograms. The skull remains incomplete, but reconstructions based on Quetzacoatlus lawsoni suggest a long, toothless beak and a possible crest. Like other Azhdarchids, it likely had stereoscopic vision, allowing it to see both forward and to the sides. Quetzalcoatlus' ecological role has been widely debated. Initially, Douglas Lawson suggested in 1975 that it scavenged like vultures, as the fossil site was far from the coast and near Alamosaurus remains. However, this was challenged due to its weak beak and stiff neck, making scavenging unlikely. Other theories emerged, such as Lev Nessov's 1984 proposal that it skim-fed like modern skimmers, though this was dismissed due to anatomical mismatches. Juan Langston later suggested it probed for invertebrates, but its small, narrow feet contradicted typical wading bird adaptations. The leading hypothesis today is terrestrial stalking, first proposed by Gregory Paul in 1987. This theory compares Quetzalcoatlus to storks or ground hornbills preying on small vertebrates. Mark Whitten and Darren Naish strongly supported this in 2008, highlighting its long limbs and downturned skull suited for terrestrial hunting. They estimated it could lift prey weighing up to 13 kilograms, while Thomas Lehman suggested Northrope was a solitary hunter. Lawsoni might have been more social, feeding in groups on small invertebrates in lake environments. Some researchers, such as Labida and Martil in 2021, argued that Azhdarchids may not have been fully terrestrial since fossils have been found in marine sediments. This contrasts with the prevailing view that they primarily inhabited plains and riparian zones. The extinction of pterosaurs, including Quetzalcoatlus, remains debated. Some argue for a gradual decline, while others suggest a sudden extinction due to the Chicxulub impact, which freed ecological niches for birds. In terms of locomotion, Azhdarchid trackways confirm that they walked with their limbs directly under their body, making them efficient terrestrial movers. They likely used a pacing gait, with limbs on one side moving together before alternating. Their flight capabilities have been controversial. Early weight estimates suggested they could soar and flap like swans or geese. However, Donald Henderson in 2010 argued that they were too heavy for flight, estimating a mass of 540 kilograms. In contrast, studies by Mike Habib and Mark Whitten suggested they could fly up to 130 kilometers per hour for thousands of kilometers using a combination of flapping and soaring. Launch mechanics have also been debated. Early studies suggested a bipedal takeoff, but later research by Habib and Whitten favored a quadrupedal launch, where Quetzalcoatlus used its strong forelimbs to propel itself into the air. However, Kevin Padian in 2021 revived the bipedal launch model, arguing that its hind limbs were strong enough for takeoff. Whitten countered that quadrupedal launch remained the most plausible method. Huayangosaurus was a small, quadrupedal herbivorous stegosaurian with a distinctive double row of vertically rising plates along its arched back. Unlike its larger relative, Stegosaurus, its plates were more spike-like, and it had two pairs of long spikes on its tail, forming a thagomizer for defense. Additionally, it possessed a long shoulder spine and smaller osteoderms along its flanks. It was one of the smallest known stegosaurians, measuring around 4 meters in length and weighing approximately 500 kilograms. Fossils of Huayangosaurus were discovered in the Deschamps Quarry in China in 1979 and 1980. In 1982, Dong Zhiming and colleagues named the species Huayangosaurus taibei, referencing the historical name for Sichuan and the poet Li Bai. The holotype consists of a partial skeleton, including a nearly complete skull and various vertebrae, limb bones, and plates. Additional specimens were later assigned to the species, though A 2006 review suggested some may belong to different taxa. Huayangosaurus is classified within the family Huayangosauridae, a basal group of stegosaurians that predates the more derived Stegosauridae. Unlike later stegosaurians, it retained premaxillary teeth at the front of its mouth, which were lost in more advanced relatives. Its skull was also broader compared to Stegosaurus. Its back plates were smaller and had less surface area than those of Stegosaurus, making them less effective for thermoregulation. However, the plates and spikes likely played a role in defense. The large spikes above its hips may have helped deter attacks from above, as it was relatively short compared to later stegosaurians. Mounted skeletons of Huayangosaurus are displayed at the Zhejiang Dinosaur Museum and the Municipal Museum of Chongqing, highlighting its significance in early stegosaurian evolution.